In this video, we're going to go over a couple of different ways to represent concentration. So the first one being percent concentration, parts per million, and then molar concentration. So far, what we have encountered the most has been molar concentration. That's the thing where we're using moles per liter to represent concentration. That's what molar concentration is. Parts per million is a way to represent concentration of very trace amounts. So you'd use this to represent the concentration of pollutants in water. Parts per million is used in toxicology to represent the concentration of contaminants. And then percent concentration is used to represent concentration in things like hand sanitizer or salt and saline solutions, that sort of thing. Okay. So the term concentration is just used to describe how much solute has been dissolved in a certain volume of solvent. And like I said, there's three common ways to express concentration: percent concentration by mass, parts per million, molar concentration. There's also a couple more outside of what we'll be talking about just down below here, and those are percent mass by mass, which is just representing the mass of your solute divided by mass of solution. And then timesing it by 100 to get it into percent. And then the other one is just percent volume by volume. So it's just volume of your solute divided by your volume of your solution times by 100. Okay, so for both of these equations, so long as the mass of your solute and the mass of your solution are in the same units, as well as your volume of solute and your volume of solution are in the same units, you can use any units. However, for the other equations that we're going to be going over, there's more specific units that we're going to have to use. So mass of solutes for the other formulas we're using have to be in grams, and then volume of solution has to be in milliliters. Okay, but in all of these cases, we're just having a ratio comparing how much solute we have to how much solution we have. Now, just as a reminder here, the solute, this is what you have less of, and it's the thing that gets dissolved when creating a solution. So I find it super helpful to just re-go over some of the terms we've already learned before we get into questions, just so that it's easier to figure out what number goes where in these formulas. Okay, so solute, thing you have less of, it's what gets dissolved. Your solvent, this is what you have more of. And it does the dissolving. And then the solution, that is just your solute plus solvent. So that's just the two of them together. So all of these equations are pretty important, especially percent by mass, parts per million, and molar concentration, which we've gone over. So molar concentration, this is the formula that is concentration is equal to moles divided by volume. Okay. So looking at our first example here, what is the percent concentration, parts per million concentration, and molar concentration for 2.100 grams of sodium chloride dissolving in 575 milliliters of water? All right, so for percent, I'm going to just clarify this. This is percent by mass. So this is percent mass by volume. So that's where we have the mass of the solute in grams divided by volume of solution, which I'm going to abbreviate solution to SOLN times by 100. All right. So filling in this equation here, my solute, that's going to be the 2.100 grams of sodium chloride because it gets dissolved in the water. Volume of solution, that's going to be the 575 milliliters times by 100. So when we take 2.1 divided by 575 and then times that by 100, what we're going to get is 0.3652. Number keeps on going on forever. And that's already in percentage. All right, so looking at my numbers here, this is in 4 sig digs and this is in 3 sig digs. So I'm going to have to go with the least amount of sig digs. So that means my final answer should be in 3 sig digs. So 1, 2, 3. Remember, leading zeros never count for significant digits. And we have 0.365%. So that's the percent by mass concentration of the solution of sodium chloride. All right, parts per million. So that formula, that's mass of solute in grams divided by volume of your solution times by 1 million. So essentially we're just plugging in the same units, or sorry, the same values into this equation. So we're going to take 2.100 grams divided by 575 milliliters times by 1 million, which once we do that, we get 3,652.1739. Number keeps on going on forever. But once again, we just have 3 sig digs because our number is given. The number with the least amount of sig digs is 3. So I go 1, 2, 3. There's my cutoff line. Now, since my cutoff line is in front of the decimal, that means that we're going to have to convert this from a regular number into scientific notation. Okay, so as a reminder for scientific notation, you only want one digit that is not 0 to the left of the decimal. So I'm going to move this decimal so that I can make that happen. So 1, 2, 3. So this is going to become 3.65. And now for the scientific notation, like 3.65 is not the same as 3,652. Okay, so to make it equivalent, we gotta go times by 10 to the power of 3. So what this last part is representing is the 3 represents how many spots we moved the decimal place. Okay, and since the 3 is positive, that tells that whoever's reading this number, it tells them that the original number that we started with is bigger than 1. Okay. So that's 3.65 times 10 to the power of 3 parts per million. Okay, so let's just write, let's see where I have room here. So that's our final answer, but I do want to write out the notes about scientific notation. We have already talked about scientific notation in a previous lesson. However, it's always good to review scientific notation since we really haven't dealt with it all too much. Okay, so scientific notation, which I'm going to abbreviate as Sci-Not. Okay, the whole purpose of scientific notation is to represent either really big numbers or really small number. Actually, I'm going to go scientific notation like that. So if you wanted to have it as a template, you would go 1 digit to the left of the decimal, and then however many digits you need after the decimal to satisfy significant digits, and then it's always times by 10 to some exponent. Okay, now for the exponents, if your original number so in this case, our original number was this one right here. Okay. So if our original number is bigger than 1, the exponent's positive. Okay. If your original number is between 0 and 1, so it's 0.825, something like that, okay? Or it's 0.0825, so on and so forth, okay? Then your exponent is going to be negative. Okay, so again, a reminder, this is just a template. Okay, you don't always have just 2 digits to the right of your decimal. Okay, it's just however many digits come after the decimal is just however many you need for significant digits. But keep in mind, you will always have 1 digit that is not 0 to the left of your decimal in scientific notation. All right, last but not least, molar concentration. So that's where we have concentration is equal to moles divided by volume. Okay, so for this, since we're given a mass of our solute, we need to first convert our mass into moles. Okay, so we need to do that by using mass is equal to moles times molar mass. But I'm going to rearrange this to isolate moles. So molar mass is multiplying moles, so I'm going to do the opposite, which is dividing. This is something you should already be fairly familiar with. So mass divided by molar mass is equal to moles. That's what we're using here. Okay, so our mass, that was 2.100 grams. Our molar mass, well, the molar mass of sodium, if you look at your periodic table, that's 2.99 grams per mole. And for chlorine, the molar mass of that is 35.45 grams per mole. So if you look up on your periodic table, that's what you're going to find for sodium as well as chlorine. Okay, so since there's only one of each, all I need to do is take 22.99 and add it with 35.45 in order to get the molar mass of this. So that is going to give me 58.44 grams per mole. Okay. So when I divide those two numbers, I get 0.0359. Number keeps on going on forever, and that's going to be moles because the grams canceled out. Okay, so keep in mind the number is has more digits than this, but I'm just writing out the first 4 digits after the decimal. But the ... means that I'm going to use the full number that I got in my calculator for the next calculation. Okay, so now that we have moles, now we can use concentration is equal to moles divided by volume. So moles, that's going to be that 0.0359 moles. I'm using the raw unrounded number for this. And then for our volume, remember that volume has to be in liters. Moles is obviously in moles, but if we look at our volume, it's given to us in milliliters. So as a reminder, to convert from milliliters to liters, we've done that a few times before. Okay, so if you want, you can look back in the videos to see how I do that. You can either use the metric conversion line, or you can just remember that in 1 liter, there's 1,000 milliliters. So ultimately, that just means we take our milliliters and divide it by 1,000. Okay, so 575 divided by 1,000 is 0.575. Okay, so when I divide those two numbers, I get 0.06249. Number keeps on going on forever, and that's moles per liter. Okay, so looking at my numbers, I got to put this into 3 sig digs. So 3 sig digs, starting by counting our significant digits from the far left. 1, 2, 3, there's my cutoff line. So I'm not counting these zeros because they are leading zeros. So 3 sig digs. So this is going to be 0.0625. And that's moles per liter. Now, if you wanted to put this in scientific notation, you absolutely can. So just to kind of humor that thought here. So scientific notation, you don't have to do this. This has the correct amount of sig digs. But if you really wanted to, put it into scientific notation. So we would go, hang on, so 0.0625. So our goal is to move the decimal so that there's only one digit that is not 0 to the left of it. So we got to move it 2 spots over to the right. So it's going to be 6.25 times 10 to the power of. Now, since our original number is between 0 and 1, our exponent is negative. And since we moved it 2 times, it's going to be -2, then moles per liter. So I still have 3 significant digits. These are the only digits that count as significant digits. The times 10 to the power of whatever exponent does not contribute to significant digits. Okay, so still have 3 sig digs, but we're just representing this as scientific notation. So you could represent your answer as this or this. Either or are correct. All right. Moving on to some other examples that I want to show you guys. So example number 2 here, I'm just going to do a couple of them to show you how this would look like, but the rest of these can be for practice. So example 2 here says, what mass of solute is found in 150 milliliters of 2.5% solution of potassium hydroxide? Okay, so this is, since they're talking about mass and volume, this is a percent mass by volume question. Okay, so percent mass by volume. So we have our mass of your solute divided by the volume of our solution times by 100. Okay, now they give us what the percent mass by volume is. Okay, so that's this part here. Okay. And the reason why I'm not doing a list of givens right now is because there's really not a lot of space for this. But if you wanted to do a list of givens, go for it. I'm just going to sneak this in and be like, this is percent mass by volume. Okay, this is going to be our volume of your solution. And we are looking for mass of solute. Okay. So what I'm going to do in this case, just to make it a little bit easier, I'm going to plug in the numbers first and then rearrange the equation. Okay, so 2.5% mass divided by 150 milliliters times by 100. Okay, so I should put percent there. All right, so the goal here is to isolate for our mass of our solute. And what I'm going to do is I'm going to essentially start peeling off the layers here, working from the outside in on the right-hand side. Okay, so what I mean by that is first I'm going to just aim to isolate this mass divided by 150. So I'm asking myself, okay, what does the 100% do to this fraction? Well, it's multiplying, so I got to divide by 100%. So the percentages, those are going to cancel out. Okay, and let's scooch this up here. So 2.5 divided by 100, that is going to give us 0.025 mass divided by 150, and that's 150 milliliters. Okay, so now it's a little bit easier to see what we need to do. 150, that is dividing into mass. Remember that your denominator, that is the thing doing your dividing. Your numerator never does your dividing. Okay, so that's why I got to multiply by my denominator. Because, again, the denominator is doing the dividing. So you got to do the opposite. So you got to multiply by the denominator. So 150, what I do to one side, got to do to the other. So 150 times by 0.025, that is going to give me 3.75. And mass is always in grams in this formula. Okay, so what I didn't write out here, so this is grams, this is milliliters, and that's from the equation that we looked at here. All right, so mass. All right, looks like the least amount of sig digs is going to be this one, because this is 2 sig digs and this is 3 sig digs. Okay, so I got to put my answer in 2 sig digs, so 1, 2, there's my cutoff line. So 3.8 grams is equal to mass. Okay, so that is our mass of our solute in the solution described in this question. All right. The next question I want to do together here is number 9. So it says determine the concentration of copper in percent by mass, so mass by mass, if 1.25 grams of copper is mixed with 27.35 grams of iron to make an alloy. So what makes this a little bit different is that now we are given 2 masses. Now, if we compare this one to the second one that we're given, okay, notice that we have less copper compared to iron. So copper is going to be our solute, whereas iron is going to be our solvent. Why? Because we have less copper and more iron. That's why. Okay. Another thing that you're going to have to look at here, so I'm going to have to write this above here. So from the first page that we looked at, so I'm using this equation here. Okay, so percent mass by mass is equal to mass of solute divided by mass of your solution. So as a reminder, solution is a different concept than solvent. Okay, solution is solute plus solvent. Okay, so you can't just put 27.35 in the denominator. Okay, you have to add your solute and your solvent together to first figure out your mass of your solution. Okay, so let's do that. So mass of solution is going to be equal to 1.25 grams plus 27.35 grams, which that is 28.60 grams. Okay, the mass of our solute, that is at 1.25 grams. Okay, let's start off with our formula. Percent mass by mass, mass of solute divided by mass of solution times by 100%. No, I didn't put the times by 100%. Okay, my bad on that. All right, so let's plug in our numbers here. So solute, 1.25 grams. Solution, that's 28.60 grams times by 100%. I'm going to have to scooch this up. So percent mass by mass, that's going to be equal to 4.37062. Number keeps on going on forever. Percent. Okay, so looks like the least amount of sig digs that I have is 3 sig digs coming from here, because this number has 4 sig digs. Okay, so 3 sig digs, 1, 2, 3. There's my cutoff line. So percent mass by mass is equal to 4.37%. Okay. So one thing that I didn't talk about as I was doing the calculation, but I did talk about on the first page of this lesson, is you got to make sure that your mass of your solute and the mass of your solution are in the same units for this formula to work out. Okay. Last but not least, we got to determine the concentration of a solution of bromine if 35.3 milliliters of bromine is mixed with 95 milliliters of water to create a solution. Okay. So with this, I'm realizing there's a typo here. Bromine, whenever it's by itself, it is one of our diatomic elements. As a reminder, the mnemonic device I use is Hofbrinkel. So BR from Brinkel, that means that bromine is diatomic. Okay, so make sure you make that adjustment. Okay, so as a reminder here, with our percent volume by volume concentration formula, that one is right here, which is what we're going to be using, okay? And all we care about is making sure that the volume of the solute and volume of solution, they are in the same units, okay? All right. So looking at our values here, we have 35.3 milliliters of bromine mixed with 95 milliliters of water. Okay, so this is our volume of our solute because we have less of it. This is our volume of our solvent. Okay, and so for our volume of our solution, we're just going to add those two together. So we're going to take 35.3 milliliters plus 95 milliliters. That is going to give us 130.3 milliliters. Okay. And I already have my volume of my solute labeled here. So if you really wanted to put that over here for your list of givens, you can. You don't have to because I already labeled it. So 35.3 milliliters. Okay, so percent volume by volume, volume of solute divided by volume of solution times by 100%. All right, so let's plug in our numbers here. 35.3 milliliters divided by 130.3 milliliters times by 100. Okay, so let's move this up. So if I take 35.3 divided by 130.3 and then multiply that by 100, what I'm going to get is percent volume by volume is equal to 27.0913. Keeps on going on forever. Okay, so looking at my numbers given, this has 3 significant digits, this has 2 significant digits, so I'm going to go with 2 significant digits. Okay, so there's my cutoff line because there's my 2 significant digits. So percent volume by volume is going to be equal to 27%.